This is networking. This is Nate Lawson and Taylor Nelson talking about exploiting remote timing attacks.
All right, let's make sure it's working. Okay, great. Yeah, as I said, we're going to talk about exploiting remote timing attacks in widespread systems. So who we are, basically Taylor and I work together at Root Labs, and we do security design and analysis for other companies. Our focus is smart cards, embedded systems, set-top boxes, game consoles, pretty much everything except most software systems. We do some software protection, DRM, and reverse engineering, so we like doing that kind of stuff. As well, crypto and protocols tend to be the glue that hold all these markets together. So I'm founder of Root Labs, and before this I was at Cryptography Research, where we also did a lot of work in side channel attacks. And while I was there, I co-designed the Blu-ray disc content protection layer. And Taylor is a Cal Poly student, which is where I also graduated from. And while at school, he works in the RFID tech lab there. But right now, he's been helping out at Root Labs. And he did a lot of the research for this talk. After spending so much time staring at picoseconds and nanoseconds and millions of samples, this quote seemed kind of appropriate. So what's a side channel, and what's a side channel attack? Basically, a side channel attack is actually where you can figure out a secret a device has, either a cryptographic key, a password, an implementation-specific secret, and basically observe the device handling that secret and figure out what that secret is. It usually requires close access, especially the first timing attacks were involving like smart cards, embedded devices where you had close access to it. But that's been improving. We're going to talk about more remote attacks. Also, it's usually non-invasive. For things like glitching or some of the work that Chris Tarnowski is doing after this session, that's invasive, where you take chips apart and use chemicals and things like that. And side channel attacks aren't invasive. There's many kinds of phenomena that leak information. For instance, the power consumed by a chip or system, the electromagnetic emissions, heat, and even sound. For instance, one of the findings that a couple research did a few years ago was that the capacitors that are part of your motherboard actually leak a little bit of sound timing or sound information based on the idle states the CPU is in. So you can actually see different rounds of a cryptographic operation based on the sound. Well, timing's different. That's what we're going to talk about today. Timing attacks are potentially exploitable from remote. Sometimes aren't, sometimes are. And usually, a timing side channel is different from these other side channels. These other side channels usually give you intermediate information about a cipher, for instance. So you might be able to observe a round key being used multiple times in different rounds of like AES or DES. Whereas with timing attacks, you usually only get the aggregate. So you get the start time and the end time, but nothing in between. Now, that's not actually true for cache timing and branch prediction attacks. We'll mention those briefly later.
All right. So how exactly do you perform a timing attack? Well, you first have to find a function that handles secret data whose timing varies based on that secret data. So after that, you're going to want to set up a client to query this server, device, whatever. And so you query it, send out the response, measure the response time, and the reply time back. Then you vary the guesses of your secret. So if you were guessing a password, you might do like A, then B, then C, then D, and so on. You want to do this a lot of times. So you got to sample a lot per guess. Oh, my bad. Sorry, guys. New here. All right. Next, you perform statistical analysis on these sampled data. So based on the target behavior of the given device or software, whatever you're targeting, you sort of make predictions based on when the guess is partially correct. Then you repeat until the entire secret is known. So this is a simple timing attack. You've got client, target. So you send out a request like 1273.
Take the timestamp.
Yeah. Response time is 1,684, whatever that is. And the delta is 411.
So this is just a simple timing attack, and you can do more sophisticated things. The main thing that people need to get from this, the main intuitive leap, is that you only need to measure the difference of response times, not the actual response time itself. So, for instance, a lot of people will say, well, when I'm pinging my server, the response time, the round trip time is on the order of milliseconds, but you're claiming to be able to attack and find differences as small as microseconds. How can that be? And the reason is because you're measuring the difference in the behavior between sets of samples, not the absolute value of what those samples, what the server did. For example, you can look at two sample subsets and say, hey, the difference of means in these two sets is 10 microseconds, but you can't really know without analyzing the server in more detail whether that was actually a 1 nanosecond difference in compute time or a 1 microsecond difference. It could be anything in between. All you know is that there is a difference and you found something significant. So a little background, local timing attacks first, since those are where timing attacks first showed up. Back in 1995, Kocher published the main paper on cryptographic timing attacks, talking about how to find the bits of an RSA private exponent by timing the entire operation. And the way he did that was he realized that it takes a different amount of time to square a value in modern processors rather than multiply values. So RSA involves both square and multiplies typically in some implementations. And a square is just shifting, and a multiply is actually a heavier weight operation. So he was able to use that to figure out the bits of the private key. That moved on most recently in 2006. Dan Bernstein of QMail fame did some simple cache timing attacks against AES. And there was a parallel result at the same time by Colin Percival about attacking RSA based on the cache behavior. And he actually did an attack called prime plus probe, where you basically have two threads running at the same time, one doing the cryptographic operation and the other one timing accesses to its own memory. And from that, deciding which cache lines were hit by the AES SBox operations. A similar attack, but optimization of that one, was the attack by Osvik, where they basically did what's called evict plus time to measure differences of the AES cache behavior. And evict plus time is a little more sophisticated. What you do is you basically evict cache lines from the CPU in a predetermined array, and then run the cryptographic operation in its entirety. And then after it's complete, you go back and remeasure access to the same cache lines and see how long it takes to access them. If it takes a long time, then obviously no one touched that page in the meanwhile. If it goes really quickly, then you know that the process you're trying to analyze or some other competing process happened to touch the same cache lines. So that's a slightly more powerful attack. I kind of think of it as like taking some photographic paper and putting an object in front of it and then shining a light on that object. You'll see a shadow created on the photographic paper, and you're sort of seeing a shadow in the cache of the operations that happened while you were waiting. And then finally, the most powerful attack of this set, using the branch target buffer. So modern CPUs have branch prediction buffers, and they use this to optimize loops and other things like that. And if you're running a series of jumps and the addresses of these jumps happen to collide in the branch target buffer with the process you're attacking, then you can actually see when the process takes or doesn't take equivalent branches. Now, moving from local timing attacks to remote timing attacks. So there's two really important papers in this series. The first one was Remote Timing Attacks Are Practical. This is the Brumley and Bonet attack on SSL in 2003. They actually were able to find the OpenSSL private key by measuring basically the time it took for OpenSSL to do a computation on that private key. And this was measuring a difference. It was actually relatively large. It was about 16 microseconds on a 1.8 gigahertz CPU. That's a large difference. Most people would think that's kind of small. And this attack was improved by a name I can't pronounce. He basically did an improvement by correlating the Montgomery table initialization in addition to measuring the timing of the exponentiation operation itself. And he's been making continual improvements in characterizing the differences of RSA operations. In this paper, they actually attacked an OpenSSL implementation over the LAN, and then they actually improved that and attacked the same OpenSSL implementation over multiple hops on their campus area network. So that was pretty impressive. And then going beyond that, the most recent paper in this series was Opportunities and Limits of Remote Timing Attacks, where Crosby and Dan Wallach, Rice University researchers, basically went out and said, let's figure out on the internet actually how exploitable timing attacks are. Let's take a bunch of different hosts and time the operations between them. We'll control every variable we can to see what's the optimal case for an attacker. And this was the first paper that actually said empirically what kinds of hosts are most vulnerable, what configurations are most vulnerable, and things like that. And a very important paper that we're going to talk about a little bit more. Basically, in this paper, what they did was they created a server that would do a delay loop. And the client could request a delay of a nanosecond or milliseconds or whatever. And the server would respond in the specified time frame. So it would also report how much time it actually took for this request to be processed. So you could actually correlate the measured response time to the server's actual calculation time. And they measured this on a bunch of different vantage points, like LAN, as well as Planet Lab, which is an overlay network. And so Planet Lab has thousands of hosts on it where people voluntarily collaborate on networking research. And so they use Planet Lab hosts to find out, what kinds of hosts are possibly vulnerable to this and how vulnerable are they. So the first interesting result was that response times aren't Gaussian. I mean, anyone here had basic statistics? Gaussian, your hump and your two tails on the side. So if you look at this distribution here from their paper, it's not Gaussian. You have basically a single peak and then a long tail off to the right. And so traditional statistical methods don't work as well when your samples aren't distributed according to the Gaussian. The vertical axis, sorry, this is a histogram. So the histogram is a count of the number of samples for each of the response times there. So the horizontal axis is latency in milliseconds. So about 15,000 samples were at that peak there. And you basically bucket based on the results. So because it's not Gaussian, the mean and median, which is typically how you do traditional statistical tests, aren't good measures. Another thing they found was that, people think, well, just take the minimum response time, right? So take a bunch of measurements, take the smallest one, and that's your estimator. This was actually shown to be not the best estimator by them as well. If you look at these different percentiles, these are basically the number of responses that came in, the response time in microseconds for the requested server processing time in microseconds. So as you can see at the far left for the 0th percentile, which is basically the minimum of the distribution, there's more noise there. But once you get to the higher percentiles, there's less noise at the lower response values. So basically, they found a lot of interesting things about network behavior. They found that actually network distance is not a good predictor of noise. So people think, well, the more hops away, the more noise you'll have. And that's partially true. If you have bad intermediate hosts in between, bad routers or whatever, you do get more jitter the farther away you are. But if you have a really awesome network, say in Sweden, it doesn't matter that it's around the world, because remember, you're measuring differences in processing time and response time, not the absolute value of these things. So even if you're far away, if you have a good network, it may be better to attack that host. A traffic shaper and other mid-layer boxes do tend to add a lot of jitter. And competing loads on the same host. So what they did was they took that same host that they're measuring and ran Apache on it and basically pounded it to 100% CPU load and found that it added about 5% unfiltered jitter to the end results versus an unloaded server. So these are some myths that people tend to have about the exploitability of timing attacks that just don't turn out to be true. In their final results, they had a really impressive number. Basically, they found that they could distinguish reliably differences of 200 nanoseconds over the LAN and 30 microseconds over the internet. And these numbers may be below what most people would think are observable. They used only 1,000 samples. When we read this paper, we thought, first of all, how could this improve with more samples? Next, what about new vantage points, such as cloud computing? If you're on EC2 and you can have servers sort of near neighbors that you don't own, what does that give, advantages does it give an attacker? And then also, for common languages, what kinds of deltas are we looking at, compared to C and Java and other things like that? So our paper, basically, or our talk, is focused mostly on several different values building on the paper from the Rice University researchers. The first one is that we try to find the smallest difference visible from common vantage points. Expanding beyond just Planet Lab, since we don't have access to Planet Lab, we decided to set up our own vantage points. So we configured a bunch of hosts, including LAN to LAN, crossover cables, EC2 to EC2 servers, and then over the internet from a commodity DSL link to EC2 and its dedicated server. We also wanted to profile different languages. So we tried some implementations of standard compare loops in C, Java, Python, Ruby, and some other languages. And we wanted to see how timeable are simple comparison loops in these languages. If you say in Python, A equal B, how long does that take to operate on an average per byte basis? And if you have an exit early type compare, which all languages do, for instance, memcomp and C, standard operators, string compares, things like that, for an optimization, they exit as soon as they find a difference. So that can provide timing information about the secret information if you're working with a secret. So we'll get into that in more detail. And then finally, we wanted to find different types of timing links in multiple implementations of various web auth protocols and, in fact, even OpenSSL. So, and then finally, we want to explain how to exploit them where possible. First question, how small a difference is visible from common vantage points? So this is just a mocked up version, but this is what you want to see. You want to see two distributions that are obviously distinct. So let's say we're comparing a password guess of A versus a password guess of B, and the correct answer is B. And the correct answer, B, is in the yellow here. This is the kind of thing you would like to see. It's easily predictable. As you can see, the two distributions are very distinct. There's very little overlap between them. And even a simple hypothesis test just based on difference of means would detect this kind of difference. What you don't want to see is this. Your two distributions are basically identical with a small number of variations. If you were to try to do hypothesis testing based on this, you'd probably find a lot of false positives, where either you'd find differences where there are none, or false negatives, where you say there are differences there, but you're keying on too small a detail, and it's actually not a good estimator. In this case, what you can do is you can take more samples. When you take more samples, often if the distributions are different, they'll separate. Or it's possible that the difference is just too small to distinguish reliably. And for instance, if you're attacking, picosecond level variations over the internet, not likely to succeed within a realistic amount of time. So people we talked to about these kinds of attacks basically had a few objections up front. One of the first things people said is, well, what about TCP and Nagel algorithm? Is that going to hurt your timing attacks? And we did some analysis of this and found that there's some simple things the client can do to avoid triggering this behavior. So basically, Nagel's algorithm works by avoiding sending small packets when you're doing lots of subsequent writes. So let's say I'm writing the message hello to the server. If I write HELLO in 5 subsequent calls, basically a poor implementation would just send 5 1-byte packets, which is a lot of overhead for TCP/IP. But what Nagel does is it says, let's delay a little bit after each small send. So if you're sending less than the window size, just wait a little while. If another send happens within that timer, then go ahead and combine the 2 sends. So that way you're reducing your overhead. But if you send a large amount of data, then it will send it immediately. So this actually had no effect on our attack because in any particular configuration, because the first packet of the response in Nagel is always sent immediately. So basically, Nagel applies to subsequent messages. So we actually found that no matter what size packet the server was sending as a response, as soon as it generated the first write call, the packet was sent. And we do need to be careful, though, to make sure that there aren't any outstanding acts from the client side, just in case that would trigger some behavior there. So what we can do is, since we can control the client, we basically connect to the server, delay for a few microseconds to make sure everything's settled down a little bit, and then begin sending the requests. Now, on the client side, you can also set an option to disable Nagel, just in case you want to be sure, but you can't affect the server, obviously. The other idea we heard from some people is, well, what about TCP timestamps? So these have been used to fingerprint hosts. You guys familiar with that? Worked a little while back? Yeah. So basically, TCP timestamps are an interesting way of observing the clock on the server side, but unfortunately, they were too low resolution for what we wanted to use them for. Most clocks on servers run about 1,000 hertz, based on the various timers for the scheduling clock, and this is just too low resolution for us. So one thing we thought of, though, possibly based on this was, what if the client could synchronize with the server's timestamp clock by just measuring it repeatedly, and then at some point basically say, okay, we know the server is going to generate a tick in the next 10 microseconds. So then send the request and check the response. If you get the old timestamp, then we got there before the tick happened, and the server responded before the tick happened. If it arrived after that point, then we'd see the next timestamp in the sequence. So this seems like it would be useful, but unfortunately it would only give probably, in our estimation, about a few microseconds of resolution, and we need to try to resolve things down into the nanosecond level. It's also very dependent on the server's timer stability. If the server ticks at a slightly slower or faster rate, maybe based on load, or based on Linux tickless scheduling or other things like that, then this might not be a reliable method. But it's still worth some more looking into, and we haven't done that yet. Some other factors we looked into, IRQ coalescing. So if you have modern gigabit hardware or faster, you usually have this feature enabled in your drivers. And what this does is basically, when your server is under heavy receive load, you don't want to be generating an interrupt for every packet you receive. That'll just overwhelm your server handling all these interrupts, and you won't get any useful work done. So instead of doing that, most drivers set up the Ethernet hardware to actually implement a state machine that says, if I haven't received another packet in a certain amount of time, then go ahead and generate an interrupt. Otherwise, wait a few microseconds or hundreds of microseconds for another packet and then deliver it. And this can add a significant amount of jitter, we found. Basically, we disabled IRQ coalescing on our client, and we also tried with our server and without the server to see how this helped in some scenarios. And this did help for some of the smaller timing variations, but didn't make much difference once you got to some of the larger values. And one thing we'd like to see more work in is more analysis of these different types of networking hardware. I mean, 10 gigabit Ethernet, really fast, low latency, fiber channel. And there's also some analysis of some of the cheaper versus more expensive gigabit adapters. Some of the cheaper ones may do poor coalescing or better. It depends on, that will depend on how exploitable it is. Also, power management. So this is something I have a little bit of experience with. I worked on the FreeBSD ACPI implementation for a long time. And CPU power management is actually quite aggressive these days, especially on servers, where you can vary the frequency and voltage of the clock rate. And then also there's these idle states, where basically you say, if the CPU is not doing anything, go ahead and put it to sleep for a while. And when an interrupt comes in, it'll wake up again and begin processing. And that's used for things like tickless scheduling. Has anyone heard that? A few people? Okay, great. Yeah, tickless scheduling is where instead of setting up your timer to tick 1,000 times a second and you're basically wasting power every time that ticks when there's not work to be done, you basically say, I know I need to handle some work in the next 10 milliseconds. So you set the timer for some point in the future and you change the rate of the timer based on your load. So these things can all affect your measurability of things, both from the server side and from the client side. So on the client side, you definitely want to disable this. What we did was we basically, we set the clock rate to the maximum on our client. We disabled all idle states. And let's see, we did some other things with SMP I'll talk about in a second. On the server side, of course, again, you can't necessarily depend on these things, but you can do some things to take advantage of it. So if you can load up the CPU's, the server CPU's workload, then the server CPU won't go to sleep, and it will tend not to throttle back its clock rate. And so you can get higher precision measurements that way. The TSC is a timestamp on CPUs, 64-bit, and it's basically one tick per clock. And the TSC isn't always the greatest timer, but it does offer really high precision. The value of the TSC may not be synchronized between CPUs on SMP host, so they may have two different values. And this causes a problem if your client is using the TSC as a timer, because let's say one is at 100,000 and the other one's 150,000, then you'll see widely varying times based on which CPU you get scheduled on. The other thing is, it may not change based on your CPU's clock rate. And so you actually want it to be reliable based on the clock rate. If the clock rate changes and the TSC rate changes in the middle and you're taking a measurement at that time, you can, again, get widely varying results. So what we did was we ran our client single CPU to eliminate scheduling problems. And the server happened to have a reliable TSC that was independent of which clock rate it was running at. And this is becoming more common in modern hardware, so that actually helps an attacker. One idea we had that we haven't seen in previous timing attacks was, what can we do about the kernel and user mode scheduling on the client side? So what we thought of was, well, let's use libpcap and have it do the timestamping of the packets for us, since that happens in the kernel right after the packet's been delivered from the Ethernet driver, but before we've run the user mode process to receive it. And so what we did was we took different measurements. One was just a raw user mode TSC measurement, where we just sent a request and then measure the response from user mode around the send and receive calls. And also in kernel mode, we changed the PCAP implementation on our client to use the TSC as the timestamp mechanism instead of the normal microtime. And these are the two distributions we found. As you can see, there's additional latency in the user mode timestamp. However, when you subtract based on the mean difference, you see this. And so we think that this kernel modification, while it was useful to us, did not provide a significant reduction in jitter. And this is the good news for the attacker, because it means you don't have to muck around the kernel too much. Just standard user mode timestamping should be sufficient. We also found this was a useful modification because a lot of times we wanted to do some additional processing on the client side to decide if we're going to look at a packet or not, and having to timestamp too close to that was a pain in the butt. So we basically relied on the kernel timestamps because the kernel will queue up the packets after they've been timestamped, and then we can just read them off at our leisure whenever we want to get around to processing them. So let's talk a little bit about noise model. The Rice paper talks a little bit about the channel noise model and estimating it, the clock skew and things like that. Basically what the noise model is, every load or pair of servers and clients will have different kinds of noise added to them. Some will have large amounts of noise with high variance. Others might have a long delay but very small variance. For instance, previously the user and kernel mode switching was a long delay but added very little jitter to our measurements. When you look at a model like this, or when you look at the measurements like this, that is usually, the model helps you select a filter. So in this case, for instance, if you look at this particular model, it's a clearly longer distribution with a second mean to it. And if you take those samples there, you basically get what looks like a Gaussian. So when you look at the distribution, that suggests a filter. In this case, I would say, knock off the upper 10 to 15% of these samples, and you'll get a better distribution to do hypothesis testing on. So we analyzed a bunch of different filtering approaches. The first one was the minimum, just basically take the minimum measured value in each set of samples. Take the quickest response time. The second one was peak filter, where basically what you do is you take the peak measurement, the most common measurement of your set, and take the mean of that set of measurements, and that is your characteristic value. The next one was percentile, where you take all the values that are less than X%. So take all the values that are in the fastest 25% of response times. And then finally, percentile range, which was take all the values between X% and Y%. From analyzing all these approaches, we thought that percentile range was actually the best approach. What this would do is it would filter out some of the really fast but high amounts of jitter in the minimum response times, as well as knock off the high end where we saw significant jitter being added. For some of our hosts, actually, the best percentiles were in the range of 2 to 25%, which we called low percentile ranges. But for some other hosts, we found that some of the middle percentiles were actually better. And that's different from what the Rice paper found. They basically focused on the low percentile and low percentile ranges. But we found that for some of the really fast response times, some of the close vantage points like crossover cable and LAN, that sometimes this was the better filter to do. So the important lesson from this is you need to not decide up front what your filter type is going to be and assume things about it, but instead measure the data and then try different ranges of filters and see what you get. Okay, going a little bit deeper here. Is anyone here familiar with differential power analysis or power analysis attacks? Oh, great. That's awesome. I wasn't expecting that. So template power analysis is an optimization of differential power analysis, where what you do is, if you're trying to discover a secret key from a device by monitoring the power consumption, there's a number of routes you can go. One is to go in completely blind and just say, I'm going to just measure the power consumption at the highest rate I can across the computation, and then try to look for varying bits based on the secret key. And that's what's called simple power analysis. Differential power analysis says take a bunch of different sets of samples and average them together and compare individual candidates against that mean. Well, template power analysis is an optimization of DPA, where what you do is you buy a similar cryptographic device. So just go get a developer kit or whatever for a particular device and program your own keys into it and measure the noise distribution while computing things with a known key. And then you go get your device you're going to attack, which has a secret key, which you don't know. And you take that filter or that template that you developed against the known keys with the similar hardware and apply that to filtering the noise for attacking the unknown key. This is a very powerful attack. It can often extract the entire key in a single trace once you've developed a good template. And what template power analysis is focused on is you have a whole bunch of different filtering approaches. You have different filter parameters, and you just brute force through them, finding which ones fit best to the particular target. We did some analysis of jitter and different host configurations. But honestly, there's a lot more work to be done in this area. We want to know what's the best filter for network jitter in certain configurations. And anyone here who's a DSP expert or knows one is welcome to contact us. We'd be interested in hearing from them. Hypothesis testing. This is how you decide whether or not you found a difference. So here's some hypothesis testing approaches we looked at. The common one, Students T, it's a basic statistics class course. Basically, what you do is you look at the difference between the means and standard deviation of two distributions. And if there's a difference which is significant to a certain level, then you decide that they're different. Otherwise, you reject the null hypothesis and say these are the same distribution. Again, it works best for Gaussian distributions. The approach we actually ended up using, Students T worked okay for some particular configurations, but not generally well. We actually implemented the box test. And the box test is based on the percentile range filters we talked about before. What you do is you create a box which it has a particular set of parameters between X and Y%. So let's say we choose 10 and 35%. For each distribution, so you've got two sets of samples, one for one guess and one for another guess, you apply the box to both of them. So you filter out the lowest 10% and you throw out the upper 65% and compare these two boxes. If the two boxes are strictly ordered, meaning the box that you expect to be less is on the left and the box you expect to be more is on the right, and they're not overlapping in any way, then you signal that as a difference. This is similar, if you could reword this as, in comparing it to percentile range filtering, you're calculating the difference between the peaks based on a percentile range filter for finding the peak. False positive and false negatives, standard thing. You want to avoid both. If you have too permissive a test, then you get false positives by saying they're different when they're not. If you have too strict a test, then you'll reject things which actually are different. So what advantages can an attacker have? A lot of people underestimate the ability of an attacker to choose an advantageous vantage point to them. Some hosts have more jitter than others, especially on the client side. We'll talk about what measurements we found, which host configurations had the most jitter. Others were extremely good, and some were good only at certain times of the day. And so when you have a high variability and unfiltered jitter, you don't want that host. If you can avoid or model the jitter in some way, let's say you know a cron job kicks off on the server at 3 a.m., you don't want to run your measurements at 3 a.m. And also traffic shapers, you want to avoid those and have as direct and clean a route to the target as possible. So the internet is quite flexible. There's a lot of different vantage points you can choose. Even if they're all the same hop count or even greater hop count away, if they have a higher quality route to the target, they may be a better vantage point. There's a paper recently called Get Off My Cloud. Has anyone read that paper or seen that talk? Basically, it talks about what kinds of allocation do cloud hosting providers like EC2 or other groups apply in deciding where your VM gets physically located. And they found two interesting results. The first one was that it was relatively easy to co-locate your VM alongside your target. What they would do is they just repeatedly launch and stop their instance until they got onto the same host. And within a few tries, usually, they would be able to get onto the same physical machine. The other thing they needed, though, to perform this attack was to be able to predict the network layout of their particular target system. So what they would do is they'd use traceroute and other mechanisms in an automated fashion to map out the network and figure out how far are they away from the desired target. And the not so surprising result was that these providers don't make any effort to prevent these kinds of things, and it was relatively easy to do so. Great paper. So we looked at a series of vantage points. The ones we looked at were localhost, guest-to-guest in a VM, crossover cable, LAN, 2 EC2 servers that were in the same region but not on the same machine, and then from a regular DSL connection to a dedicated server, and then finally from there to an EC2 server as well. Here are our results. These are the minimum delays that were visible for us for each vantage point based on a certain number of samples. This will change based on how many samples you're able to take. So a few things about these results. The first things we did was we made sure to hold the false positive and false negative rate below 5% for our filter selection. And we used the box test with the parameters chosen by brute force between 0 and 95%. So we actually took all of our samples and 4 different sets of samples and ran it through And what our box test brute force selector would do is randomly choose subsets of samples from the original set. So this was actually a sample size of 10,000 samples, and we configured the parameter selector for 9,000 samples. And what it would do is we would do 200 runs, selecting a random 9,000 set of samples from each distribution, and run the hypothesis test. If they were the same files, same sets of samples to begin with, and the filter said there's a difference, then that was a false positive, and we counted that against the filter. If, on the other hand, they were two different sets of samples, and it said there's no difference, then we counted that as a false negative. And what we want to do, again, is hold the false positive, false negative rate below 5%, which was 10 out of 200. So for the most optimal filters for each configuration, the parameter settings were different. So for instance, for localhost, it selected different parameter values than for the crossover cable. And what we assume is that an attacker can profile either that host or similar hosts in the same style as templated DPA attacks. The attacker can basically find some other service it can query or something to be able to choose known values and decide how well they can attack unknown values. So for localhost and crossover cable, both were about less than 25 nanoseconds predictability. And then for LAN, it was about 40 nanoseconds. And we ran many, many tests to confirm that indeed these were reliable. These are somewhat conservative estimates. We had some measurements that were, say, about half or more of these values, but we rejected them because they weren't reliable. A lot of times we would be able to distinguish it with the desired false positive and false negative rate, and other times we couldn't distinguish it. So rather than report too optimistic values, we reported conservative values. As you can see here, the EC2 to EC2 numbers were the highest in varying. We were able to resolve reliably down to 15 nanoseconds for repeated data sets, but only at certain times. So it must have been something to do, we think, with some of the scheduling on the same host or other competing loads or something. But basically, that value had the most variance. However, when it was good, it was very good, even better than some of our LAN measurements. So we think Amazon must have some really nice networking hardware up there. And for our dedicated hosts, it was actually very poor. We thought by getting a dedicated host, it would be idle and we'd be able to get good measurements. But it turned out the provider of that host had put it on a network that wasn't the best and had a decent amount of jitter, possibly due to firewalling. And so we only were able to resolve about 4 milliseconds, which is really bad compared to our other WAN tests. Again, DSL to EC2, we could reliably distinguish 20 microsecond differences. So then what we did was we cranked up the sample rate. And we haven't finished taking samples for all the data sets, but at least for the LAN, we were able to improve pretty significantly our results. So first of all, 500,000 samples sounds really big, but it doesn't take very long. On a LAN, it took about 15 minutes for each run of 500,000 samples. And what we found was that we were able to improve it to about 15 nanoseconds distinguishability by selecting 490,000 from the 500,000 samples and doing false positive and false negative testing. However, these numbers are still subject to review because we need to finish testing and taking more samples. The key thing to note here is that we were able to get a factor of almost 3 improvement just by taking more samples. So if in doubt, just take more samples. Early on, we had to reject a lot of samples. And what we found was that after doing some debugging and testing, we found that our own firewall was actually screwing up our internet measurements. So here are 2 distributions. One was a measurement of a 25 microsecond delta without the firewall, that's in black, and then the other one was with the firewall. As you can see, the firewall adds not only a significant amount of delay, the peaks are shifted by a few milliseconds, but also that adds a lot of jitter. The distribution gets shorter and wider. So if you have any problems, if you want to do any client attacks, what you want to do is do them from outside the firewall. Also, EC2 is really awesome when it's not noisy, but it can be really bad when it is. Certain sets of our samples were completely unusable, and we think this could be due to competing VMs. While the Rice University talk focused on competing processes on the same physical box, for instance, scheduling Apache processes, we think that the scheduling algorithm or something related to the Xen hypervisor that's used by EC2 may be more dangerous to taking good samples. However, when we did get good results, we would often get runs that were entirely composed of good results. And in those cases, it was comparable to our quiet LAN, in fact, often better than our quiet LAN. So they had better hardware there. Here's a distribution where you can kind of see the clear distinguishability of the two distributions there. We actually had a few things, strange things, continuing to happen along the way. The first one was that we ended up with a lot of noise that was added by the interpreter startup. So when we profiled different languages, Java, C, etc., C, of course, had very low overhead. But starting a Java VM is actually a pretty noisy event and would tend to disrupt our first few measurements of that system. We saw weird caching behavior. We're still not sure about exactly what those are related to. Possibly related to CPU caching and possibly related to CPU scheduling behavior. We ran into something earlier on where the equal and not equal operators in terms of comparisons seem to be behaving differently. And we had some questions about maybe that if in a particular language, if they're comparing strings with equals, it starts from the beginning. And if you're comparing with not equals, it starts from the end, because we kept seeing inverted samples. But it just turned out that we weren't taking enough samples for that particular configuration. So let's look now. We've looked at vantage points and said, okay, what's the minimal distinguishability from different vantage points for a given number of samples? Let's look at comparisons in different languages and see how exploitable these are. So we took some just basic CPU tests of a comparison operator in multiple languages and multiple types of comparisons. And what we did was we generated a TSC delta for a 1-byte comparison difference. So one value would be A, and the next would be AB, for instance. And we would see how long that took in terms of difference between just the A versus AB. So the interesting thing that we found here with C is that C, with the default settings, GCC compiles in its own built-in operators for memcomp. And memcomp is actually really slow in GCC. It's actually turns out to be a rep comp SB for the entire string. When we disabled built-ins, compile it with no built-ins, and ran it on the same host, we got a much faster compare. And we disassembled it and found that the compare was a quad word size compare for up to 8-byte quantities, followed by a rep comp SB for their trailing bytes. So the libc or the equivalent in Windows are both good memcomp implementations customized for the particular architecture, better than the built-in GCC values. So for instance, for GCC built-ins, it took about 719 picoseconds per byte, whereas in the no built-ins, it was about 89 picoseconds per byte, much faster. Next, we looked at Java. Java was honestly the slowest of everything we looked at. For the Sun JDK6 and running string.equals on 2 values, we found it took on average about 40 nanoseconds per byte. And the arrays.equals, even though it's suggested as an optimization to most people, is actually slower than string.equals. And yeah, I'm not sure why that was exactly, but we did some looking into the source code for JDK, and they both seem to be pretty straightforward for loops. In the case of the string.equals, it just does for the length of the string. If char A is not equal to char B, return. And so it's a native type. And then for the arrays.equals, it did comparisons of the individual byte values against each other. Again, we're not sure why arrays.equals was slower for byte arrays. It should be equivalent to chars. We actually do have one theory about that in the next slide. For Python, we also compared 2 different things. We compared string equals, which is the most common way people do it. And just for comparison's sake, we also compared list equals. And the difference in bytes for string equals was about 1.4 nanoseconds per byte, which compares favorably to the naive C implementation. And then for list equals is about 10 times slower. So that's definitely not the way to go. For Ruby, we also found it was similar to C memcomp. And PHP was too difficult to analyze with the built-in timer because it only gave microsecond level resolution. But looking at the implementation with source code analysis, we saw that it used C memcomp as well. So basically, for all these languages except for Java, all the interpreted languages tend to devolve to a C memcomp for comparing byte arrays or strings. Java is a notable exception there. So we looked at Java a little more, and it was clearly the slowest, but we wanted to see how it would scale with clock rate changes. Some people don't have servers that are as fast as others, some have faster servers. And we found that the comparison rate per byte tended to scale linearly with the clock rate, as you expect. But the interesting thing about this was that all of them were still much slower than the other languages. And all of these appear to be exploitable over the LAN, but not the internet. We're dealing with 43 to 144 nanoseconds average per byte. In more detail, the array equals, sorry, that's actually backwards. Array equals byte was actually was slower than string equals. That's correct, actually. So string equals, for instance, for individual bytes, we looked at what does it do for the first byte and the second byte and the third and fourth. And string equals is pretty fast. It starts off a little quicker than others, about 9 nanoseconds for the first byte difference, and then 88, 30, and 34. But it was still much faster than the array equals. The worst case was array equals with object arrays. And if you don't have a byte buffer you're passing into array equals, it'll actually devolve to an individual method call on every object, basically saying if object 1 dot equals object 2, go to the next one. If object 1 object equals object 2. And that's the worst case. Now, we didn't find any libraries that actually used this particular method, but that's something to avoid if you're an implementer. Looking at the array equal behavior, we were wondering why it seemed to be faster than string equals. And what we found was an interesting thing where it appeared to have this sort of stepping behavior between the first, second, third, and fourth bytes, where it appeared that every 16 bits, it would be slower, and the subsequent byte would be faster. And we think it's possible. We haven't analyzed in detail or disassembled it fully to understand why, but it appears to be fetching data in 2-byte quantities. And this is most visible at the full clock speed, where it takes 80 nanoseconds for the first byte, then only 5 for the second, then 80, and then 5. And this can actually help an attacker later on. We'll talk about that. Another interesting thing we found was that base 64 compares, we think they're more vulnerable than just a regular comparison of the binary data itself. And if you look at some of these libraries we looked at, some of these web frameworks, that often they'll compare the base 64 encoded value, the base 64 encoded string, against the other base 64 encoded string. And with base 64, as you know, you're taking 8 bits and you're cramming it into 6 bits. And so this is great for sending an email or over a text interface, but it's not so great if you're trying to avoid easy exploitability for attackers. So in this case, this actually gives attackers a 4 times advantage because you're revealing 6 bits for every byte the attacker tries to guess. And so they only have to try 64 values before advancing on to the next one. Also, there's an additional timing leak that base 64 encoding offers, where if you're taking a secret value and encoding it base 64, it will branch differently based on the value that you're encoding, whether it expands it into a subsequent byte or not. And so in this case, you're leaking approximately the Hamming weight of all the bytes that you're encoding during the encoding process. So we didn't attack that, but that might be something to look into later. All right, so now let's take all this stuff we've learned. We've looked at different vantage points, and we've said, what's the different delays? And we'll have some thematic music for this from Star Wars. Thanks, Felix. I'll come to your talk later. All right, so we've looked at different vantage points, and we said, what delays are visible from different vantage points? We've looked at different languages and said, hey, what looks exploitable? So we've looked at Java and said, hey, Java looks exploitable from the LAN. It's from 40 nanoseconds varying up to 180, depending on how fast you're... All right, this is great. I love it. Yeah, so we've looked at different vantage points. We've looked at different compare functions. And let's look at actually attacking HMAC. So a little more background on attacking HMAC. Some of the first attacks against HMAC were documented in 2007 and in terms of timing attacks. So the first one that was publicly released was an attack against the Xbox 360 bootloader. In this case, the Xbox 360, during its bootloader process, would verify an HMAC on a particular bit of code and then decide whether or not to run it or not. And in this case, based on whether the HMAC was correct or not that the attacker had supplied, each byte would take additional 2.2 milliseconds to compare. And this is very visible from local, since you have full physical access to your game console. Another announcement was in the Google Kezar library, which is a multiple language implementation of various cryptographic things for web toolkits. And it had a timable HMAC comparison. Then Sun's JDK6, message digest equals function, Java Bouncy Castle, Mozilla's NSS TLS session ticket, which we'll talk about more in a minute, and then finally an OAuth 1.0 HMAC verification. That was actually Sebastian Martini. I got the name wrong on that one. So exactly what is an HMAC and why would it be vulnerable to timing attacks? So in this case, what happens is a server will generate a token for the user. In the most basic case, this is used for things like session IDs. This is used for like single sign-on. It's used for OAuth, OpenID, and other processes where you want to give the client something which they can't modify. So the server wants to generate a ticket for the client. They want the client to give it back to them unmodified at some point in the future. If the client does modify it or try to forge it, you want to know about it. So what you do is you take a hash function, and hash functions aren't normally designed to work with secret keys. So you use a construction called HMAC, which combines a bunch of data and a secret key and gets a hash result from it that's a keyed hash result. You take the ticket you want to sign, and you apply the HMAC with your given server secret key to that data, and then you append this authenticator value to it, basically like a signature. And then on the validation side, why this would be subject to timing attacks is that the server has to generate the correct HMAC for a given message in order to compare them and see if they're not equal. So on the server side, you know the secret, right? The attacker supplies you a message, or the legitimate client. You calculate the HMAC using the correct key over this ticket, and then you just compare the two, right? If they are the same, then the ticket was unmodified. If they're different, then someone's messing around with you. So web authentication frameworks. Anyone here familiar with OAuth, OpenID? You use them? Anyone implemented OAuth or OpenID? There's quite a few implementations out here. So these frameworks allow two different things. They have two different purposes. OAuth was designed with the purpose of allowing a client to authenticate themselves to the server to access various APIs on the server. So the client and the server actually share the same secret, and the client can send requests to the server, like delete my Flickr photo album or whatever. And you sign it with an HMAC, and if the request validates, then the server says, sure, this user has this correct HMAC, go ahead and do whatever they asked me to do. This is used all over the place. Pretty much every web API that allows the client to sign some kind of requests has a mode of allowing HMAC. OpenID is slightly different. OpenID is a way of allowing a user to authenticate to one website with another website performing the authentication for the relying party. So in this case, the third party basically signs a token that says, yes, this user logged in correctly with their password. Go ahead and let them into your site. So those are the two different methods of using OAuth and OpenID. And like I said, they're both, OAuth is more common and is growing in volume. OpenID isn't used as much, but is supported by a lot of people already. So we went and actually reviewed the source code for these implementations and found a lot were potentially vulnerable to simple compare timing attacks. Basically, everyone who looked at these things and said, hey, we've got two values. We're going to check if they're equal, the correct HMAC value and the one the attacker or client supplied us. Let's just do equal equals or string.equals or arrays.equals on them, and that's our result. We actually found that dozens of implementations were vulnerable to this. And when we notified them, some decided to fix it and some did not. So exploiting timing attacks. We implemented a number of different ways of exploiting this. The simplest way we came up with, which we haven't seen anyone else do yet, was to iterate over the byte that you're guessing. And you generate a bunch of samples for a particular byte, sending it to the server. You measure the time that it takes, then you iterate over your guesses. If you're lucky, it takes on average about 128 guesses per byte, because since there's 256 if you're unlucky. And what we did was we implemented an approach called iterative guessing. Whereas you remember before on the Java arrays.equals, for instance, you have a mechanism where the first byte that's correct takes 80 nanoseconds longer, and then the second one takes 5 nanoseconds, then 80, and then 5. So the second one is much more difficult to distinguish than the first one. But what we can do is iterative guessing, where you walk forward past it, you take the best guess at a particular level of samples, and you assume that's correct. Then you move forward from that and try it against the next guess. And if you get a confirmation, then you'll see an even wider difference between the two distributions. If you got it incorrect, you won't see any difference between the two. And we found that's actually successful with a lot of systems like this where there's a small number of multi-byte variances between things. It doesn't work, for instance, if you have a 32 or 64-bit compare, because you'd have to be generating 4 billion different values for each sort of incorrect guess you walk forward with. We didn't go out and attack production websites, just to be clear. We did not attack Google or Amazon or others. Instead, we just sent them an email saying, hey, we found these flaws in open source implementations of these toolkits and you use similar things. Why don't you just check your own servers for it? And we figure that if they wanted us to test it, they would have asked us to. And if we tested it without being invited, then they might consider it an attack, where basically we're generating lots and lots of invalid requests. If they happen to see this, no one actually logs incorrect HMAC results, but if they did see this, they might think that we're trying to attack them. And also, we don't own the server, so we don't have permission to that. So it's up to them to review their own code. And at least one major provider that wasn't listed above actually confirmed that they are vulnerable and that they used a common open source implementation. So they are in the process of fixing that, and hopefully it should be deployed already. Countermeasures to timing attacks. The naive countermeasure most people come up with when they first hear about it is let's add noise. If you follow some of the threads that are on the OpenID list, some of the first things people said is, well, we'll just add random delays or whatever. And it sounds good at first. So you're looking at a graph and you're like, hey, it seems like we can do something about this. So let's start with the first. This is without noise. And then we add a bunch of noise for a certain number of samples. So we say, like, here's 500 samples with, I think you added like between 0 and 1.5 milliseconds of noise to this randomly. Sorry, 150 nanoseconds of noise to each of these. So on the order of the delta between them, we basically could double the value or add nothing to a value depending on the random choice we made. So as you can see, this distribution looks pretty random. And more importantly, you can't distinguish the black from the yellow, right? There's a lot of overlap where it's brown, but there's no clear distinguishing factor. But let's just take some more samples. So while still adding noise, we increased it to 1,000 samples. As you can see, the distributions are starting to look more like they did originally. And then we took 5,000 samples. Again, these still have noise added to them. But as you can see, the two peaks are starting to separate out clearly. There's kind of an outline of black on the left and an outline of yellow on the right. And then finally, with 10,000 samples, as you can see, you have almost identically to the original distribution. So adding noise does not do a good job of preventing timing attacks. It only requires the attacker to take a few more samples. A fix that we recommended to a lot of people on these mailing lists was a simple constant time compare loop. This used to be an interview question we would use, but since we revealed it to everybody, it's no longer an interview question. So this is in C, but the equivalent works in Python or Java or whatever. Basically what you do is you check the length first, and then if you go walk through all the bytes in the array and you just compare them and you XOR them together. If there's a difference between them, you'll get a non-zero value, and if there's no difference, you'll get 0. And each time you accumulate using OR. So the important thing about this code is that it doesn't generate any conditional branches that are varying based on the secret data that you're comparing. And there's a few things about this. The first thing we got back from a few people was, hey, this is a lot slower in some of our interpreted languages. The particular example someone used was .NET. And what they were saying is, hey, in .NET, a normal comparison devolves to C memcomp. And this particular loop implementation, of course, is implemented in bytecode, and so isn't quite as fast. They found it was about, I think, 10 times slower than a memcomp. But if you remember, the memcomp probably is not your bottleneck on your server. If it is, you're handling a ton of requests, you probably need another server. And then second of all, it's probably better to not be exploitable than to be a little faster and insecure. Absolutely, yeah, definitely. The HMAC hashing operation takes a lot more CPU horsepower than the comparison. But depending on whether that's implemented in native code or not, it may vary. So that could be a problem, and it could affect some implementations, and it's worth some investigation, but we don't think that's a good enough reason not to fix this bug. So OpenSSL. I was set to put some slides in here, and I was trying to decide whether or not to put these in or not. So I decided to tell the story instead. Yes? Yes. By the way, we're going to have questions answered at the end as well. Yes, Sun did fix their JDK implementation in update 17, I believe, or 18 of JDK 6. It's either 17 or 18. And they changed their message digest equals to be basically that code that we showed. So OpenSSL. So we went after like OAuth and OpenID, and we found nearly every implementation. There's dozens out there, first of all, so it took forever to review them. And we found nearly every implementation had this timing leak in them. A few people had actually a year ago, when we had originally given a talk based on timing attacks at Google, talking about the Kezar flaw and others, they had originally fixed, I think it was one of the Java OpenID implementations. Can't remember which one it was, but anyway, so they fixed a few of them. So some of the maintainers took it upon themselves to fix that, and that's great. A lot of other people said, it's too small a difference, we don't care about it. So that continues to this day. So the story of OpenSSL. So OpenSSL has this thing called session tickets. It's in TLS 1.0 spec. It's an extension. What happens with SSL is you have this thing called your session state. You can do things like resuming sessions. And resuming a session is basically what you do is, instead of doing all that key exchange and heavyweight public key crypto operations, you say, I as a client would like to use that same key that I negotiated with you, server, a few minutes ago. When you do multiple HTTP requests, for instance, with your browser, it will implement this SSL session resuming. And this is perfectly fine. It's perfectly secure. You're just saying, I want to use that key that I already know about. If either the client or the server don't actually know the key, so if one of them was trying to lie about this resume, they can just force a renegotiation back to a new key. So people wanted to optimize SSL, and in the TLS 1.0 spec, there's this thing called session tickets. So normally what has to happen is the server has to keep all this session state in memory or in a disk cache or somewhere, so that if the client decides to resume it within a particular time window, that it has the secrets available for it. And that's okay for normal servers. It's not that much data. It's a few hundred bytes, less than a kilobyte probably. But for embedded systems, this was a problem because they'd have to have lots of RAM to keep all these sessions around if they're being used as a server. So session tickets was is an optimization of that. What you do is the server takes the session state for the client, and after the client has negotiated a key with it, encrypts that with a key known only to the server, and then HMACs it, also with a key known only to the server, and sends this off to the client. And the client has the option, if it supports this extension, of saying, hey, here's this session ticket that you handed me a few minutes ago, let's reuse that session. And the server will say either, okay, I'll do it, or no, I don't like this result. For instance, if the HMAC doesn't validate, it's not supposed to allow the client to select that key. Well, of course, we went and looked at OpenSSL and found that they were using memcomp. So the standards see memcomp to verify the HMAC result of session tickets. And session tickets are enabled by default in OpenSSL as well. So we contacted them and actually said, hey, you might want to use this particular comparison loop. And it was about 3 weeks ago. And they said, no thanks. We think it's too small. And we said, well, it is very small. It is C. We found that the C variations was around 800 picoseconds to a few nanoseconds on our server. And we don't think this is exploitable over the internet for sure. Possibly exploitable in LAN situations, but mostly we don't know because these configurations are highly dependent on the particular servers and network that's involved. So as we found in our measurements, and as the Rice University researchers found as well, some configurations are extremely visible. We found a factor of 4 in our variations of the EC2 measurements, where we could actually see much smaller differences. So we suggested they fix it a few times, and they came up with various reasons why they didn't want to fix it. So today, it's still not fixed, actually. OpenSSL is unpatched, and it's an interesting challenge. We have not exploited it yet, but we'd be interested in seeing if anyone else out there can exploit it. Mozilla chose to fix this about in October of last year. So NSS is secure against this attack, and we hope that OpenSSL will eventually fix it. So let's see. Any questions? Yes? We haven't looked at GNU TLS. So we looked at NSS and OpenSSL and found OpenSSL hadn't fixed it, GNU TLS had. So based on this, there's a couple different attacks we think should be more successful against the OpenSSL HMAC verification. One of them is some of the branch target buffer prediction stuff, where if you're on the same server or if you're on the same EC2 server, this is something you should be able to take advantage of as a side channel. It's very powerful and it gives you intermediate results. We think that it may be a profitable way to go to measure the branch prediction of the HMAC compare loop. And we think that normal cache timing attacks probably won't be successful because the HMAC value is relatively small. It's about 20 bytes. So that tends to fit within a cache line. Whereas with AES, your tables are spread all over different cache lines. And so AES and RSA are much more visible from a cache timing attack. So it'll be interesting to see what people can do. Yes? That's a very good question. So the question was, is the normal Unix password comparison function vulnerable to this kind of thing? And the answer is mostly not. So in the case of a plain text password, one of the things that we talk to some people about is they say, well, what about plain text passwords? And yes, of course, plain text passwords are definitely vulnerable to this kind of attack. You shouldn't be using plain text passwords for lots of reasons, but that's just another one. So for hashing your password and then comparing the hashes of it, what's nice about that is being able to do a timing attack doesn't help the attacker in that situation because it's iteratively exponentially more difficult to create a given hash to match the particular value on the server. So for the first few bits, it's very easy. It only takes 256 tries at most to collide in the first 8 bits. But after that, then it takes another factor of 2 to the 8 multiplied by that and accumulate until ultimately you're doing about 2 to the 160 work for SHA-1 or equivalent for whatever cipher you're using for your password hashing routine. So that becomes infeasible. There is a combined attack that was a pretty interesting idea that Tim Newsham came up with that was based on attacking Unix password hashes. And what it is, it's a combined online and offline attack where you use, because of the salt, for instance, if you want to do a partially online attack against a password, you can use a timing attack to gain information about the salt and some bits of the hash, maybe the first 8 bits. And at that point, you can do offline analysis and brute forcing of the password. And if you find that it doesn't hash to the same 8 bits in the first byte, then you reject that and don't even bother sending it to the server as a candidate test. And this can help you eliminate, if you're doing a dictionary attack, for instance, large quantities of your dictionary. But it doesn't reveal the password directly. Yes? Oh, okay. Any other questions? Yes? It was message digest equals. So in the case of HMAC, the message digest is the underlying primitive. And that was fixed in Sun's update 17. But not every distribution has rolled out this new version, so there are still a lot of vulnerable implementations. Definitely. So of all the languages we looked at, Java's comparison functions were by far the most visible in terms of timing deltas. They had from around 43 to 45 nanoseconds average byte differences, and then sometimes much greater. For instance, at 800 megahertz, we saw between 120 and 180 nanoseconds, which was visible from most local configurations we could come up with. Yes. That's a good question. So he was saying, is there maybe a way you can mislead the attacker by supplying fake hash values or whatever? So it's probably best not to build something so complicated, but I can think of some ways that might be helpful. For instance, if you're getting numerous HMAC validation problems, say more than one from a given host, then something weird is going on. HMACs don't just fail to validate. Either your server has major memory corruption problems or an attack is going on. Those are the only real 2 things that could be happening. And in those cases, you really want to know about it. So you should probably log it if you get something like this, because it should almost never happen. And then, yes, you could say if one IP address, for instance, is sending repeated incorrect HMACs, you could just compare it against garbage data by hashing something somewhere and rehashing it or whatever. And at that point, they would never succeed. And that might be good for honeypots, for instance.
I was thinking, is there a way to animate value that will eventually give them a key that they can't use?
Yes, of course. You just compare it against, like I said, a hash of some garbage data somewhere, and just keep using that same garbage data for that same IP address or same attacker. In that case, they'll eventually discover the garbage data, but it won't be useful for them. Yes? So stalling responses to HMAC failures. So the naive way to do that is to only stall if the HMAC is incorrect, otherwise let them in immediately. And so that's easy to detect because you just send your request, wait the required deadline, and then terminate the connection with a reset if they've stalled because you got it incorrect. And that's one way to keep people from being able to log in as that user. But it can help slow down the timing attack in this case because you really want to measure that timing delta in the response. So if you add a constant time, say 1 millisecond to every invalid HMAC response, the attacker does have to wait that long. But the attacker can just parallelize this attack by using multiple clients and lots of parallel connections at the same time. And that can usually defeat any kind of delay-based countermeasures. Don't reply at all in the case of bad data. That's true. I have to think about that a little bit, see if there's any flaws in that. But that certainly wouldn't be able to give them timing information about what type of bad data they had. Another thing you can do is just set a flag and then later on return a general failure at some point so that it's not distinguishable time-wise from that, or there's more things that happen in between. But really, the problem is that you're kind of hiding the delta, but the delta is still there. So at some point, the server will execute a deterministic path and return a response of some kind. At that point, the delta between the two responses may be visible, may not. It's better to use constant time and then add things like logging or maybe delays or something like that as a subsequent countermeasure, not the primary one. Okay, thank you very much.